This is Nikilian, Assistant Professor, Department of Civil Engineering, AIT Mangalore. So today in this session, I am going to discuss about deflection of prestressed concrete members. So in our first session, I had discussed about what are the different types of losses and what is a deflection and what are the different types of deflection that will occur in a prestressed concrete beam. So today, before solving some of the numericals, let us try to recall what are the formulas required for the calculation of deflection of a beam under different loading cases. So firstly, what is a deflection? So deflection means it is the change of the shape of a prestressed concrete beam. That is, the beam will undergo deformation when the load is applied on a beam, and that is called as a deflection. So as per IS recommendation, the deflection is having certain limitations. For example, if the deflection is in upward direction, then the deflection limit is span by 300. If the deflection is in downward direction, then the limit for deflection is L by 250 is the deflection limits, where L is nothing but is the span of a beam. So let us see what is deflection. So deflection is calculated for service loads. Since a prestressed concrete member is smaller in depth than an equivalent reinforced concrete member, the deflection of prestressed concrete members tends to be larger. Hence, the calculation of deflection becomes necessary when the members are shallow. So we know that the prestressed concrete members are having very shallow depths compared to the reinforced concrete member. So here what happens, as the depth of a members are very small or shallow, we need to know the deflection of a beam or a member. Hence it is very necessary to calculate what is the deflection that will occur under loading condition of a beam. So here the deflection of prestressed concrete beam can occur in three loading cases, whereas if we consider a normal beam, a normal or a conventional concrete beam, there in that case the deflection will occur only for two cases. One is for dead load and another one is for live load, whereas in case of prestressed concrete members, the deflection will occur for three cases. So what is the three cases? So the deflection occurs due to prestressed cable, deflection will occur due to dead load, deflection will occur due to live load. So these are the three cases under which the prestressed concrete beam will undergo deflection. Now firstly, let us see what is the deflection that will be taking place under prestressed cables. So we all know that when the cables are prestressed, the cables will undergo change in length. So change in length means when these cables are tensioned, there is increase in the length of cable, and after anchoring the cable at the edges or ends, the cable will try to regain its original shape and size. So during this process, what will happen? The PSC members will undergo change in shape. That is, the PSC members will undergo auging bending moment. The beam will undergo auging. Hence, there is a change in the shape of a beam due to the prestressed cables. Hence, we need to calculate what is the change in beam. So that is called as deflection. So firstly, let us consider deflection in beams with straight tendon. So here I will consider a beam. So here I will consider a rectangular beam. let depth be d and length be L. So this cable is provided with an eccentricity of E. Hence the cable is having a constant eccentricity throughout its span. And here, due to the eccentricity of a cable, there is a bending moment induced in a beam. So what is that bending moment? We all know that moment is equal to force into perpendicular distance. So here the force is applied along this cable, and this cable is having an eccentricity of E with respect to the CG of a member. Therefore, moment is equal to force into perpendicular distance. So force into eccentricity, that is P into E. So here in this figure you can see, in the second figure you can see bending moment diagram. So this is the bending moment diagram for the cable which is having an eccentricity of E throughout its span, or this is the bending moment diagram for a beam which is provided with a straight cable with an eccentricity of E. So to calculate the deflection of this type of beam, we have a ratio, that is delta is equal to moment of area of BMD for half span about the support divided by flexural rigidity. So that will be equal to delta is equal to PE L square by 8EI. So from your exam point of view, it is sufficient if you remember this final equations. So if you want to know how we got this equation, so it is nothing but it is the moment of BMD for half of the span about the support. So this is the support. So taking moment of this BMD for half of the span, we will get this delta. So this is the BMD. So length of the beam is L and area of this bending moment diagram is P into E. So here you can see this is P into E. So if I take a moment of this BMD about the support for half of the span, then what will be the moment of this BMD about half of the span? So I will take the moment about the support. So moment will be area of this BMD for half of the span is PE into L by 2. So span is L, so half of the span will be L by 2. So PE into L by 2, that is the area. Then what will be the moment of area? So moment will be L by 2 into 1 by 2, that will be L by 4. Therefore delta is equal to PE into L by 2 into L by 4 divided by flexural rigidity EI. So the final equation will be PEL square by 8EI. So this is how the equation for delta is derived. Taking moment about the support for half of the span of bending moment diagram, we will get what is delta. So this is the equation for a beam which is provided with a straight tendon with an eccentricity of E. Now let us see what is the deflection equation for a trapezoidal cable profile. So here you can see a rectangular beam. So a rectangular beam of span L and depth E. So this beam is provided with a trapezoidal cable. So this is the cable profile. So at the midspan, the cable is having an eccentricity of E, and at the supports or at the ends, the eccentricity of the cable is 0. So here the cable is bent at a distance of L by 3. So here the cable is bent at a distance of L by 3 on either side, and it is made to meet the support at an eccentricity of 0. Then let us consider the length of this bent cable from here to here as L1, and from this bent portion to center of a beam as L2. So from here to here it is L, and the remaining length up to the center is L2. So if I draw bending moment diagram for this condition, I will get a BMD like this. So this is the bending moment diagram for this condition. And if I want to calculate the equation for deflection, that is delta. So delta is equal to moment of area of BMD for half span about the support by flexural rigidity. That is taking moment of the area about half of the span about the support. That means, so this will be half of the span. So taking moment of the area about half of the span. So taking the moment of this rectangular area and taking the moment of this triangular area about this support, we will get this equation. That is delta is equal to PE by EI into 2L1 square plus 3L2 square plus 6L1 L2. So this is the equation you should remember to calculate the deflection of a beam which is provided with a trapezoidal cable profile. So if it is difficult to remember this equation, then remember this ratio. Remember the ratio, that is delta is equal to moment of area of BMD for half span about the support by flexural rigidity. Now let us go to the third case. Deflection in beams with parabolic tendons. In previous slides, we saw a beam with a straight cable or a linear cable. And in this slide, we are seeing a cable profile which is parabolic. So here, let us consider the first case. Deflection in beams with parabolic tendons centrally anchored. Centrally anchored means here it is a rectangular beam of length L and depth D, which is provided with the cable, and the cable profile is a parabolic where the eccentricity of the cable at the midspan is E and eccentricity of the cable at the supports is 0. So this cable is subjected to a tensile force of P. So you can see here the cable is subjected to a tensile force of P with an eccentricity of E. Then what will be the bending moment of this? So bending moment of this is nothing but P into E, that is force into eccentricity, P into E. So at the support there is no eccentricity, so P into eccentricity, that support is 0, P into 0, it is 0. So here you can see the bending moment diagram. In the bending moment diagram, the bending moment at supports here and here it is 0, and bending moment at the midspan is P into E, force into eccentricity. The eccentricity is E at the midspan, so at the midspan the bending moment is P into E. So to calculate the deflection for this type of beam, take the moment about the support for the half span of a bending moment diagram. So here you can see moment of area of BMD for half span about the support divided by flexural rigidity. That is delta is equal to what is the bending moment, what is the moment of the area of this 50% of a BMD about the support. That will use delta is equal to 5 PEL square by 48 EI. Now coming to the second case. So here deflection in beams with parabolic tendon eccentrically anchored. So here you can see a beam of length L and depth of D. Here the cable profile is a parabolic cable profile, and make a note that the cable profile is having an eccentricity of E1 at the midspan. At the midspan, the eccentricity of the cable is E1, and here at the supports, the cable is having an eccentricity of E2. Here the eccentricity of the cable at the support is E2. Similarly, on the other side, the eccentricity of cable is E2. So if you want to use this equation for this condition, then you should remember that the eccentricity at midspan is E1 and eccentricity of support is E2. So if you make a confusion as eccentricity of support as E1 and this midspan as E2, then this equation changes. So this is the equation developed for the eccentricity of midspan as E1 and for the eccentricity of the support as E2. So for this condition, this equation is developed. So here we will get two bending moments, or we can split the bending moments into two components. One is, I will consider the bending moment diagram due to parabolic tendon, that is I will consider due to this eccentricity. So I am going to consider this for only the parabolic tendon. So for this, the moment will be P into E1 plus E2. So the moment will be P into E1 plus E2, that is force into eccentricity. So here the force is applied along this end from here, that is here and here, and the perpendicular distance from the force and the center eccentricity is E1 plus E2. From here to here it is E2, and from here to here it is E1. Therefore the moment due to the midspan eccentricity is P into E1 plus E2. So you can see in the second diagram. So P into E1 plus E2, and it is a parabolic bending moment. Now coming to the eccentricity of the support. So if I consider the eccentricity of the support, then the moment developed due to this eccentricity of the supports will be P into E2. So the eccentricity at the support is E2, and here it is P is the force applied. So the moment is equal to P into perpendicular distance P into E2, that is P into E2. We will get a bending moment diagram like this. So if I take the moment of area of 50% of the span of this, and if I take the moment of area of 50% of the span of this, then the final equation what I will get is delta is equal to PL square by 48 EI into 5 E1 minus E2. So don't make a confusion of taking this as E2 and taking this as E1. So if you want to use this equation, then this should be E1 and this should be E2. Then only this formula is correct. So if I take moment of this about the support, then it will be 2 by 3 into L by 2 into P E1 plus E2, that is the area, and centroidal distance is 5 by 8 into L by 2, that is the centroidal distance. For this, if I take the moment of the area, then it will be L by 2 into PE2 into L by 4, that is the centroidal distance. We will get the final equation as this. Now coming to the fourth case, deflection in beams with sloping tendons eccentrically anchored. In the second case, we add a cable which was a sloping cable or a cable having a trapezoidal profile, but here the cable is linear, which is having two eccentricities. The eccentricity at the midspan is E1 and eccentricity at the supports is E2. So here also we will get two bending moments. One bending moment is due to the eccentricity E1 and other bending moment is due to eccentricity E2. So if I draw a bending moment for E1, so bending moment or moment about centroidal axis is force into perpendicular distance. So at the midspan, the perpendicular distance will be E1 plus E2. So E1 is this, and the remaining distance from here to here is E2. Therefore moment is force. Force is P and perpendicular distance is E1 from here to here, and from here to force into E2 from here to here it is E2 plus E1. here. Therefore, the moment with respect to midspan is equal to P into E1 plus E2. So for this, the bending moment is this one. So bending moment at the supports is 0 for this, and bending moment at the midspan is maximum, that is P into E1 plus E2. Now considering the bending moment diagram for the eccentricity of the supports. So with respect to the support, we have eccentricity of E2. So eccentricity is E2 and force is P. Therefore moment is force into perpendicular distance. Perpendicular distance is this eccentricity. So that is P into E2. So this is the bending moment diagram for eccentricity E2 at the support. So if I want to calculate the deflection, then this is the formula. Delta is equal to P L square by 24 EI into 2 E1 minus E2. So this formula is obtained. This formula is obtained by taking the moment of the area of 50% of the span about the support of this bending moment, and taking the moment of area of 50% of the span about this support. So adding this both, you will get this final equation. So here also you should not make any confusion regarding the eccentricity. So this should be E1 and the end eccentricities should be E2. Then only this formula can be used satisfactorily. If you take this as E2 and if you take this as E1, then here the formula changes. This will be E2 and this will be E1. So remember the conditions. So E1 at midspan, E2 at the supports, then this formula is suitable. Now coming to the fifth case, deflection in beams with parabolic and straight tendons eccentrically anchored. So here it is a rectangular beam which is provided with a cable, and cable profile is having two nature. One is the cable is straight at the midspan. From here to here it is straight profile, and here it is parabolic. You can see here it is parabolic. We can tell that the length L1 is parabolic and L2 is linear or straight cable. So bending moment for this cables is this one. So here the eccentricity at the midspan is E and eccentricity at the support is 0. Therefore the maximum eccentricity at the midspan will be P into E, that is moment is equal to force into perpendicular distance, that is P. So this will be the bending moment diagram, and this is the formula to calculate the deflection. So here also this formula is obtained by taking the moment about the support for half of the span, by taking the moment of this area and taking the moment of this area about the support. So here you can see the centroidal distance of this area and centroidal distance of this area with respect to the support. Now sixth case, deflection in beams with parabolic and straight tendons eccentrically anchored. So in previous case the cable was having two profile, that is linear or straight in the mid from ear to ear, and from ear to ear it is parabolic. So here also the condition is same, but only the difference is in previous case eccentricity at the supports were 0. Here the eccentricity is 0, but here at the supports we have an eccentricity. So let us consider the eccentricity of the supports as E2 and eccentricity at the midspan as E1. So remember, eccentricity at the supports here and here it is E2, and eccentricity at the midspan, that is this one, is E1. And if I draw a bending moment diagram for this, so to draw a bending moment diagram, as I told in the previous condition, we can split the BMD into two cases. One is we can draw a BMD for the eccentricity of the midspan, and we can draw BMD for the eccentricity at the supports. So first let us consider BMD for the eccentricity of midspan. So BMD for the eccentricity of midspan will be P into E1 plus E2. So the force is applied here. The distance between perpendicular distance between force and midspan is E1 plus E2. Therefore, moment is P into E1 plus E2. So this is the bending moment diagram for the eccentricity of the midspan. Now considering the eccentricity of the supports. So the eccentricity at the support is E2. So the perpendicular distance between the force and the the force and the centroidal axis is E2. So from here to here it is E2. Therefore, moment is equal to force into eccentricity E2. That is P into E2. We will get the bending moment like this. So to calculate the deflection of this beam, we will use the equation delta is equal to P into E1 plus E2 by 12 EI into 5L1 square plus 6L2 square plus 12L1 L2 minus PE2 L2 square by 8 EI. So this is the final equation which is obtained by taking the moment of area, by taking the moment of this and this area about this support, and by taking the moment of 50% of the area of this bending moment diagram about this support, and by adding both we will get this final equation for this type of cable. So these are the 6 cases which you should remember for calculating the deflection of a beam which is induced due to the tensioning of tendons or tensioning of cables. Now let us see what's the deflection in a beam that will occur due to self weight as well as due to the live load which is imposed on a beam. So firstly let us consider deflection due to dead load. So we all know that dead load or self weight of a member is always a UDL and that will be constant. The self weight or dead load of a member is constant and it is always a UDL and it will not change. So we have two cases for deflection due to dead load. One is when a beam or when a member is simply supported member. So you deal with simply supported member. Then the formula to calculate deflection is 5WL to the power 4 by 384 EI. So this is for a simply supported beam with UDL. And one more condition is a cantilever beam with UDL. Then for this the formula is WL to the power 4 by 8 EI. So these are only the two cases used for the calculation of deflection of a prestressed concrete member when it is subjected for a dead load. Now the second case, deflection due to live load. So as I said you, dead load is in the form of UDL, it is always constant, whereas live load. So live load, it can be a concentrated load, or it can be a series of concentrated loads, or it can be a UDL, or it can be a uniformly varying load. So live load means we have different types of live loads. So here we have some equations for different cases. If I want to calculate a deflection for a simply supported beam and the live load acting on that simply supported beam is in the form of UDL, then in such case the formula is 5WL to the power 4 by 384 EI. Suppose a beam or a member is a cantilever member and the live load acting on that cantilever member is UDL. Then the formula to calculate the deflection is WL to the power 4 by 8 EI. Suppose a member is simply supported beam or a simply supported member, and the live load which is imposed on that member is a concentrated load or a point load, then the formula to calculate the deflection of that member is WL³ by 48 EI. Similarly, a cantilever beam and the live load acting on a cantilever beam is point load, and this point load is acting at free end. Then the formula to calculate deflection due to live load is WL³ by 3 EI. Similarly, for 2-point loads, the formula to calculate deflection is 23 WL³ by 648 EI. 23 WL³ by 648 EI. So these are the different equations that you should remember for the calculation of deflection under different conditions. So here the most important thing to remember is the equations or formulas of deflection due to prestress, the equations or formulas due to dead load, and equation or formulas due to live load. So these are the equations which you should remember. So note, so till now I told you the different formulas which are used for the calculation of deflection. Suppose if it is difficult to remember the formulas, then how to derive the formula to calculate the deflection? So as I told you in the beginning of this session, we can calculate the deflection of symmetrically loaded and simply supported beams at midspan or mid-span point are directly obtained from second moment area theorem. Suppose if a member is more complicated, if the member is involving unsymmetrical loading, then for this case the deflection can be calculated by combining both the theorems of moment area. That is, by combining first moment area theorem and second moment area theorem, we can derive the equation for deflection for a beam which is subjected for a loading and that load is unsymmetrical. So deflection, in a simple way we can define deflection is equal to area into x bar divided by EI. So here there is a simple example. So here it is a simply supported beam which is subjected to 3-point loads. So for this beam the bending moment is shown here. So this is the bending moment diagram for this beam. So here if I want to calculate the deflection, then the deflection is equal to moment of 50% of area of a BMD. So this is the midspan, here it is the midspan, so considering 50%, that means this shaded area is 50% of this BMD, and taking the moment of this shaded area about the support, about this support, considering the moment of the 50% of the area, we will get deflection of this beam which is subjected to 3-point loads. Now coming to the next point. So total deflection. So how the total deflection is calculated? So total deflection is calculated in two ways. One is short-term deflection at the transfer and other one is long-term deflection under service loads. So short-term deflection means it includes deflection due to live load, dead load, and deflection due to prestress. So long-term deflection under service loads means it will include deflection due to live load, deflection due to dead load, deflection due to prestress, and deflection due to the average of prestress by considering losses of prestress. So considering losses of prestress means we are going to consider all the losses that will occur in a member and we will take the average of that losses and initial prestress and we will calculate the deflection. So here we have a formula for short-term deflection and long-term deflection. So short-term deflection, this is the formula: loss due to dead load, live load, and pre-stress. For long-term deflection, this is the formula, and here the explanation of these terms are given. What is delta PO? What is delta PE? PE delta DL, delta SL, delta LL. So all the explanation of this terms are given. So this formula is used when we are going to consider the different losses. For example, a question is given to calculate a long-term deflection, and in that question they have given a creep coefficient, they have given a shrinkage coefficient, they have given a loss due to relaxation of a steel. Then we will calculate the different losses, and in such condition we can use this formula. Suppose they have not given any data regarding creep of concrete, shrinkage of concrete, relaxation of steel, etc. Then we are going to use this equation to calculate the long-term loss. So here delta load means this is delta load means it is the deflection due to live load and dead load. Delta PS deflection due to pre-stress into loss ratio. So if loss ratio is not given, consider loss ratio as 0.85. Remember, if loss ratio is not given, consider loss ratio as 0.85 into 1 plus 5, where 5 is creep of concrete. If creep of concrete is not given, then consider creep of concrete between 1.5 to 2. So these are the equations to calculate long-term deflection and short-term deflection. And this are two equations to calculate long-term deflection. So this is the equation which is used to calculate long-term deflection when different losses are considered. This is the formula to calculate long-term deflection when the losses are not considered or when the data regarding the losses are not given. Now let us try to solve some numericals on deflection. So let us consider first example. A concrete beam with rectangular section 300 mm wide and 500 mm deep is pre-stressed by two post-tension cables of area 600 mm square each, initially stressed to 1600 Newton per mm square. The cables are located at a constant eccentricity of 100 mm throughout the length of the beam, having a span of 10 meter. The modulus of elasticity of steel and concrete is 210 and 38 kN per mm square respectively. A. Neglecting all the losses, find the deflection at the center of span when it is supporting its own weight. Condition B. Allowing for 20% loss in pre-stress, find the final deflection at center of a span when it carries an imposed load of 18 kN per meter and DC is equal to 24 kN per meter cube. So here DC is nothing but density of concrete is 24 kN per meter cube. So here a concrete beam which is a rectangular section is pre-stressed by two cables, and cable of area of each cable is 600 mm square, and each cable is initially stressed to 1600 Newton per mm square. And here the cables are having an eccentricity of 100 millimeter. And we should note that the eccentricity is constant throughout the length. So constant throughout the length means it is understood that the beam is having an straight cable or a straight tendon, and the span of a beam is 10 meters. Young's modulus for steel and concrete is given. So here he has given two conditions. First one is neglecting all the losses. We should find the deflection at the mid-span by considering its own weight and pre-stress. And the second case is we should consider a loss of 20% in pre-stressing, and we should calculate the deflection at the center when the beam is subjected for a live load or imposed load of 18 kilonewton per meter. So these are the two conditions which we need to calculate. So as I said you, it is a beam with a straight cable. So this is understood by reading the question. So first let us consider self weight of a beam. So let us consider self weight of a beam as G. So we know that self weight of a beam is equal to cross sectional area of a beam into density. We will get self weight. So cross section area of a beam is 300 mm by 500 mm. In terms of meters, it is 0.3 into 0.5. This is the cross section area of a beam multiplied by density of concrete 24 kilonewton per meter cube. We will get 3.6 kilonewton per meter. So self weight of a beam is 3.6 kilonewton per meter. If I convert this into kilonewton per millimeter, it will be 0.0036 kilonewton per millimeter. So how to convert this in terms of kilonewton per millimeter is 3.6 divided by 10 to the power of 4. So if I further substitute that, it will become 3.6 into 10 to the power of minus 4. That will be equal to 0.0036 kilonewton per mm. And moment of inertia I. Moment of inertia is equal to 300 into 500 cube by 12. That is BD cube by 12. That is equal to 33,125 10 to the power of 6 mm to the power 4. And next is pre-stressing force. So in the question, they have given what is the area of each cable and what is the stress applied to the, or what is the stress induced in each cable. So the cross section of area of each cable is 600 mm square, and each cable is imparted with a stress of 1600 Newton per mm square. Therefore, what will be the force? We know the ratio of stress is equal to force by area. Then force is equal to stress into area. So by using that concept, 2 means 2 number of cables, 600 is the area of each cable into 1600 is the stress induced in each cable. Therefore, the total pre-stressing force which is induced into 2 cables is equal to 1920 into 10 to the power of 3 Newton, or 1920 kilonewton. So by seeing the formula, we will come to know what are the data we need to calculate. See, for example, we have a formula for a downward deflection due to self weight. So due to self weight, always the deflection will be in downward direction. So what is the formula to calculate the deflection due to self weight? It is 5gl to the power 4 divided by 384 EI. So G is self weight, so we need to calculate self weight. L is span, EI is rigidity modulus, it is given. So here ELP, so P is pre-stressing force applied to the cables. So first we should check what are the data required to substitute in the formulas, and we should first calculate those data and we should substitute in the formula. So we have calculated what is the self weight of a beam, and we have calculated what is the pre-stressing force induced into the cables, and I'll just substitute the values in the formula. So deflection due to self weight is equal to 5gl to the power 4 by 384 EI. So 5g we have calculated in the first step. L in terms of millimeter, it is 10 into 1000 to the power 4. 384 EI into 38 into 3125 into 10 to the power of 6. So here it is being converted into kilonewton per millimeter square EI, which is equal to 3.95 millimeter. So here, due to self weight, the beam is undergoing a deflection of 3.95 millimeter, and this deflection will be in downward direction. So this deflection is occurring at a midspan and it is a downward direction. It is acting in downward direction, or we can tell that the deflection is of a sagging type. Hence, I will consider this deflection as plus 3.95 millimeter because the deflection is of sagging type. It is towards downward direction. Now considering deflection due to prestressing force. So the deflection due to prestressing force is always in upward direction, because when the cable is tensioned and anchored, the cable will try to regain its original shape and size. So during this process, what will happen? The cable will undergo hogging shape. So hogging shape means the deflection will be in upward direction. Therefore, upward direction due to pre-stressing force is equal to 4PE square by 8EI. So this is the deflection formula which is obtained by considering moment of area about the support for the 50% of a BMD. So substituting the values which we have already calculated, the value of PEL and EI, we will get the deflection due to pre-stressing force. It is 20.2 millimeter. So it is an upward deflection. So the first condition is neglecting all the losses, find the deflection at the center of a span where it is supports its own weight. So the beam is supporting its own weight along with the pre-stressing force. Then what will be the net deflection in upward direction? So the net deflection will be 20.2 minus 3.5. It will be 16.3 mm in upward direction. Or you can also substitute this as minus 20.3 plus 3.9 is equal to minus 16.3 mm. So here the minus 16.3 mm indicates the deflection is in upward direction. Or else you can also substitute as 20.2 minus 3.9, which is equal to 16.3 mm. But here you should write the deflection is in upward direction. So same thing is written here. Upward deflection of a beam when it supports its own weight, 20.2 minus 3.9 is equal to 16.3 mm. Or if you consider this 20 as minus and this as plus, because as I said, the upward deflection it is always negative because it is in hogging shape, and that deflection is developed due to the compressive forces, and so it is negative, and sagging bending moment is always in downward direction and it is positive. So you can also consider this as negative and this as positive, so that the final answer will be minus 16.3 mm. So there that minus indicates upward deflection. Now coming to the second case. What is the second case he has asked? So allowing for 20% loss in the prestress, find the final deflection at the center of a span when it carries an imposed load of 18 kN per meter. So now the beam is also subjected for a live load of 18 kN at midspan. So to calculate the bending moment due to live load, or to calculate the deflection due to live load, is 3.9 into 18 by 3.6 is equal to 19.5. So how it is means, so it is given it is carrying an imposed load of 18 kN per meter. So 18 kN per meter means that is indicating that the live load is UDL. So here the bending moment is also the deflection due to self weight is 3.95. So by using this deflection 3.95, so using that concept we are calculating downward deflection due to live load, or else we can also directly use this equation 5GL to the power 4 by 384 EI. We can also use this formula to calculate the deflection due to live load as the live load is UDL. So here it is representing that 3.9 is the deflection due to dead load, and 18 is the intensity of live load, and 3.6 is the intensity of dead load. So we can tell that for a dead load of 3.6 kilonewton per meter, the deflection is 3.9. Then what will be the deflection if the UDL is 18 kilonewton per meter? So if the UDL is 18 kilonewton per meter, then the deflection is 19.5 mm. So if you can't remember this condition, or if it is difficult to remember this condition, we can also use this equation, same formula, to calculate the deflection due to live load when it is a UDL. So here I will tell you once again. Here what I have done is I have taken the comparison of live load and dead load. So here for a dead load of 3.6 kilonewton per meter, the deflection is 3.9 millimeter. Then what will be the deflection for 18 kilonewton per meter? So for 18 kilonewton per meter, the deflection will be 9.5 mm in downward direction, because the live load will be always acting in downward direction, hence the deflection will be in same direction. So he has given that if there is a loss of 80%, then what will be the net deflection? So by considering upward deflection due to prestress after loss is equal to 0.8 into 20.2. So what is that 0.8? So 0.8 is allowing for 20% loss in prestress. So out of 100%, if the loss is 20%, then the remaining prestress in the cable is 80%. So 80 divided by 100, you will get 0.8. So that is 0.8, and deflection of prestressing force is equal to 20.2. So 20.2. That means when the cable is having a prestress of only 80%, what will be the deflection? So that will be 16.16 millimeter. Therefore, the final deflection of a beam due to self-weight, prestress, or live load is equal to plus 3.95 minus 16.16. That is, this is a deflection in upward direction, and deflection in upward direction means it will be like this, like this, like this. That means it is in a hogging shape. That means it is a negative. So minus 16.16 plus 19.50. 19.50 is the deflection due to live load, and it is in downward direction. That means the deflection will be like this. So it is like a sagging deflection. That means it is plus. Therefore, the total deflection is 7.29 mm. So here the positive sign is indicating that the deflection, net deflection, is in downward direction. Now let us consider a second example. So a concrete beam with cross-sectional area of 32 into 10 to the power of 3 millimeter square and a radius of gyration of 72 mm is pre-stressed by a parabolic cable carrying an effective stress of 1000 Newton per millimeter square. The span of beam is 8 meter. The cable, composed of 6 wires of 7 mm diameter, has an eccentricity of 50 mm at the center and 0 at the supports. Neglecting all losses, find the central deflection of a beam as follows. Case 1, self-weight plus prestress and self-weight plus prestress plus live load of 2 kN per meter. Thus, in this problem, a concrete beam with a cross-sectional area 32 into 10 to the power of 3 mm square is having a radius of gyration of 72 mm, and it is having a parabolic cable profile which is having effective stress of 1000 Newton per mm square. Span of a beam is 8 meter. Cable is having 6 wires and diameter of each wire is 7 mm. And here the cable is A parabolic cable which is having an eccentricity of 0 mm at the supports and eccentricity of 50 mm at the midspan. So for this case, we have to determine what's the deflection due to self-weight and pre-stress, and what's the deflection due to self-weight, pre-stress and a live load of 2 kN per meter. So this problem is same as previous problem. So firstly, we know what are the formulas that we are going to use to calculate the deflections due to pre-stress, deflection due to live load and deflection due to dead load. So by remembering the formula, first we shall calculate what are the data required to substitute in the formula. So we need self weight, we need modulus of rigidity, we need moment of inertia, and we need what is the deflection or what is the eccentricity. So first let us consider Young's modulus. So in the question, Young's modulus is not given and density of concrete is not given. So let us assume Young's modulus of steel as 38 kN per millimeter square and density of concrete as 24 kN per meter cube. So density of concrete we should assume to calculate self weight of a member. Therefore, first area is given 32 into 10 to the power of 3 mm square. I is given, that is it is not moment of inertia, so they have given radius of gyration, it is 72 mm, span is 8 meter, that is 8000 millimeter, eccentricity is 50 millimeter. Therefore moment of inertia I is equal to A into I square, area into radius of gyration. So using this equation we can calculate what is the moment of inertia. Moment of inertia is equal to area 32 into 10 to the power of 3 into 72 square. 72 is radius of gyration square. Therefore, moment of inertia is equal to 166 into 10 to the power of 6 mm to the power 4. And pre-stressing force P is required. In a given question, they have given number of cables used and what is the initial pre-stress induced in the cable. So using this we can calculate what is the pre-stressing force. So 6 into 3, 6 into 38.5 into 1000. So 6 is wires. So 38.5 is the area of each wire into 1000. 1000 is the initial stress which applied to the cable. So 38 means it is pi d square by 4. So pi into 7 square by 4 will get 38.5. Therefore, initial pre-stressing force is equal to 23 into 10 to the power of 4 Newton, that is 231 kilonewton. This is the initial pre-stressing force which is applied to the cable. Next, let us calculate self weight of a beam, that is G. So G, self weight of a beam is equal to 32 into 10 to the power of 3 by 10 to the power of 6, that is 32 into 10 to the power of 3 is the cross section area of a beam and it is given in terms of millimeter to the power 2 into 24. So 24 is density of concrete, what we have assumed it is 24 into 24 kilonewton per meter cube. So here 10 to the power 6, it is nothing but here 24 kilonewton per meter cube is converted into 24 kilonewton per millimeter cube. So 1 meter is equal to 10 to the power of 3. Therefore, 1 meter is equal to 10 to the power of 2. Therefore, meter cube means it is 10 to the power of 2 into 3. That gives us 10 to the power of 6. Therefore, the final answer is equal to 0.77 kilonewton per meter. By converting this into millimeter is equal to 0.00077 kilonewton per mm. So this is the self weight of a member. Now considering the first condition. In first condition, they have asked us to calculate self weight plus pre-stress. So I will calculate what will be the deflection due to the self weight. So deflection due to self weight is equal to 5gl to the power 4 by 384 EI. So remember, self weight of a beam or a member is always a UDL. So for a UDL, to calculate the deflection, this is the equation, is equal to, substitute the values of G, L, E and I, we will get 6.5 millimeter. So it is 6.5 millimeter. The positive sign is indicating that the deflection is in downward direction. Now I will calculate the deflection due to pre-stressing force. So as I said you earlier, the deflection due to pre-stressing force is always in upward direction because the stresses developed in the cable will be of compressive nature, hence the deflection will be always in upward direction and hence it is considered as negative. So upward deflection due to pre-stressing force is equal to 5 PEL square by 48 EI. P is nothing but initial pre-stressing force, E is eccentricity, L is span, EI is modulus of rigidity. So substituting the values. So 5 231 kilonewton, 50 mm is the eccentricity at the mid span, 8000 is the span of a beam, 48, and this is the rigidity modulus in terms of kilonewton per millimeter square. Therefore deflection is 12.2 millimeter. So here we can also write as minus 12.2 millimeter because it is a upward deflection. So here I have shown this as plus 12.2 because here I have mentioned upward deflection due to pre-stressing force, hence if I write as 12.2 mm it is correct. Suppose if I am not using this term upward, then I should use negative sign here. So now calculating the deflection due to live load. So downward deflection due to live load. So due to live load, the deflection is always in downward direction because the live load is acting in downward direction and the given live load is 2 kilonewton per meter. So here self weight of a member is 0.77 kilonewton per meter and deflection due to self weight of 0.77 kilonewton per meter is 6.5. 6.5 mm is the deflection of a beam due to a self weight of 0.77 kilonewton per meter. Then what will be the deflection of a beam for 2 meter? Sorry, what will be the deflection of a beam for 2 kilonewton per meter live load? So that will be equal to 16.9 mm. So you can also use this equation. We can also use this equation to calculate the deflection due to live load when the live load is UDL. So here the live load is UDL, hence we can also use this equation to calculate the deflection due to live load, or else we can also calculate by interpolating the values of deflection due to self weight and live load. So first condition is what is the deflection due to self weight and pre-stress. So deflection due to self weight and pre-stress is 12.2 minus 6.5, which is equal to 5.7 mm. So upward deflection, or else we can also substitute this as minus 12.2 plus 6.7, we will get an answer as minus 7.5 mm. So that minus is indicating upward deflection. So in such case this term is not required to be mentioned as upward. Second case is deflection due to self weight plus pre-stress plus live load. So deflection due to self weight is 6.5 mm, deflection due to pre-stress 12.2. So 12.2, it is upward deflection like this. So upward deflection means it is considered as negative because it is due to compression, plus 16.9. 16.9 is the deflection due to live load. So due to live load, the deflection will be in downward direction. It will be like this. That is sagging deflection, hence it is plus. Therefore total deflection is equal to 11.2 mm. So it is plus 11.2 mm. That plus sign indicates the deflection is downward direction.